This is Ryan Rainville with AMSC's Network Planning and Applications Group. I'm going to demonstrate a method for finding the best place to install AMSC's VVO StatCom in order to fix high voltage or low voltage issues on a distribution circuit. So this example circuit was provided to AMSC from a utility that had a voltage recorder on the middle of the feeder, and at certain times of day it was recording high voltage, and at other times of day it was recording low voltage. So to familiarize with the layout of this feeder, the source is here near the green marker in the northeast corner, and this is a 25 kV circuit that extends approximately 46 miles until the three-phase ends in the southwest corner. The next step is we want to identify elements that can influence the voltage on this feeder. So the pink markers are identifying voltage regulators. And the most important two regulators are this first regulator along the main three-phase and this second three-phase regulator bank along the main line. Next, there's distributed generation on this feeder. These 6 markers are indicating wind turbines for a total of about 3.8 MVA in generation. And the yellow marker is a run-of-river hydroelectric facility. So these are intermittent generation sources not under the control of the utility, and they're contributing to the voltage variability across this feeder. If there were shunt capacitors in the circuit, that's an additional item that would want to identify here. The last element to identify is load and the distribution of load. So it's helpful to apply the load density map. And you can see that there's a concentration of load near the end of this circuit. So that's likely to cause voltage drop issues as you're trying to serve that load current through the cumulative impedance of the upstream conductor. So now that we've identified the influences to voltage, we'll run 2 load flow scenarios. The first load flow scenario is maximum load with minimum distributed generation. So load is 100% P, 100% Q, and the controls for all generators are disabled, but the regulators are performing the normal tap operations, and we've applied a target voltage range of 95% to 105%. So you can see that there's significant undervoltage below 95% in the middle of the feeder, and then also a little on this single-phase tap that's served near the end of the three-phase circuit. Another way to look at this would be to plot the voltage profile across the main line three-phase. So this result box is locked near this load center at the end of the circuit, and we can plot a per unit voltage profile from there tracing back to the source. So you can see that the voltage drop continues down the circuit, and the first regulator has to raise its tap significantly to elevate the voltage, but then the voltage drop across its regulation zone is significant. The second regulator also has to raise its tap significantly to bring voltage back within the healthy range. So the first regulation zone, the voltage drop is from approximately 1.04 per unit to 0.9 per unit, or more than 10%. So since the regulator, a typical regulator can boost up to 10%, you could not resolve this voltage issue with a different type of control setting at the regulator. You'll either create high voltage on the front end of this regulation zone or have this remaining low voltage at the tail end of the regulation zone. So the next step is to run the second load flow, which is minimum load with maximum DG, and this should present the other voltage extreme on the circuit. We're going to assume minimum load is 30% of peak load, and we've restored all of the distributed generation on this feeder. So here you can see significant overvoltages above 105% in green. And again, we can plot the voltage profile from the end of the feeder, and you'll see that most of this high voltage is occurring at the end of the first regulation zone. And so when we compare these two voltage profiles, we see that most of the voltage extremes are happening between mile 18 and mile 28. And you can actually go on these profiles and right-click, and it'll take you to a location along the feeder. So that's a helpful suggestion of where you should place a VVO device. Because the VVO, since it can both operate inductively or capacitively, it can both lower the voltage and raise the voltage using its control mode. So I've already selected two places to install VVOs, and I'll identify those with these black markers. But presently, they're disabled. So I'll go and re-enable these. And you'll notice that there's a step-up transformer in each of the VVOs. The VVOs can directly connect to circuits that operate at 11 kV through 13.8 kV. For voltages above that, you need a step-up transformer. So here we're assuming a 1000 kVA transformer with typical impedances of 5.5% and an XR of 8. The VVO itself will be on a volt-var profile. And this video won't cover the specifics of selecting the volt-var profile, but we have both VVOs on separate volt-var profiles, and both of them are monitoring the 25 kV node, this node on the high side of the VVO step-up transformer. So to determine how much the VVO is going to influence voltage, it's important to know the stiffness of the system at that location. A conventional regulator will provide up to 10% boost or buck. How much the VVO will boost or buck voltage is dependent upon the stiffness of the system at the location that you're installing the VVO. So a helpful measure of that is fault power and XR ratio. So you can apply a short circuit, and using the keywords LLLMVA, which is three-phase fault power, and X1R1, which is the XR ratio, you can get a determination of the stiffness of the system where you're applying the VVO. So in general, the VVO can be helpful for voltage regulation where the fault power is below 50 MVA, and the higher the XR ratio, the better. In this case, the fault power is around 28 MVA, XR of 1.6 at the first VVO location, and 23 MVA, XR of 1.5 at the second. So I would approximate that each VVO will provide about 3% booster buck at their respective locations. And when we look at the magnitude of overvoltage here, we're using two VVOs because the overvoltage is in excess of 3%. So in addition to adding these two VVO units, we should look at if there's improvements to regulator controls as well. This upstream regulator here has a locked forward control mode, which means that it will stop tapping when it senses reverse current from excess generation downline. If it's possible within your regulator control, it may be preferable to use a cogeneration control mode, and you can consult the regulator control manual for the specific implementation. In addition, because the VVOs are going to be helping flattening the voltage profile, we can lower the voltage target of this regulator. So now that we've made those improvements, we'll rerun the two load flow scenarios with the VVOs added. You want to make sure that the VAR compensator controls are enabled because that's the representation in SIME for the VVO device. So for the max load condition, you can see that most of the undervoltage has been resolved. And if we rerun the voltage profile from the end of the three-phase to the beginning of the circuit, you can see that the entire mainline three-phase has been brought within the target voltage range. And also the regulators do not have to tap quite as high to maintain healthy voltage. So the presence of the VVO, the two VVOs, is reducing the workload on the existing regulators. The second load flow is the minimum load with maximum DG, again making sure that you have the VAR compensator checked. And you can see that almost all of the overvoltages have been resolved in this light load condition as well. And that can be confirmed along the main line using the voltage profile plot. So the voltage profile across the feeder has been significantly flattened with the VVOs, and the two regulators do not have to tap that significantly away from their nominal position to maintain a flat voltage profile. So these two VVOs have enabled the hosting of 3.8 MVA in distributed wind generation without the associated voltage violations. They've reduced the number of tap change operations required on the existing regulators. They've avoided the need to add additional regulators or additional capacitors. And they're also improving the power factor of this circuit as measured at the feeder breaker during the peak loading conditions. And because these two VVOs are providing a solution for voltage problems, they're also providing an alternative to reconductoring. Often, if voltage issues can't be solved with regulators or capacitors, a planner will look at reconductoring, which could be an expensive solution. The 2 VVO option is relatively economical. So hopefully this demonstration has been helpful. If you have questions about a specific application for the VVO, please feel free to reach out to AMSC's Network Planning and Applications group.